Morning, Year 9. Sorry I'm not there again today. Unfortunately, I've been off most this week since about Monday lunchtime, and I've currently got a fever, so I'm just not fit to be in work. But because it's hit your lesson so much, I didn't want to leave you doing more practice, so I've decided to go through and do a lesson, make a video going through the last topic that you guys haven't done in simultaneous equations, which is solving them graphically. I don't think you should find this too much of a challenge, hopefully, because we've done a lot of practice on straight line graphs recently when we were doing graphical inequalities. So I'll just talk you through this in this video, and then hopefully you should have a booklet that is available for you to work through. The first half will be just graphical simultaneous equations, and you can do everything apart from question 8 and 9 in the booklet. The 8 and 9 will need to be done in your red books because there's no graph available. And the second half is just a mixture of simultaneous equations. So solving normal ones with elimination, where you have amounts of x and y, and also quadratic ones as well. Okay? So, like I say, you shouldn't find this too challenging, hopefully. So the main thing is you plot both of these on a graph, as you might be able to guess. So the first equation, the one in red, is in the form y equals mx plus c, because we have y plus something x plus or minus something. So this is a gradient intercept kind of plot I would do. So I start off when I'm doing gradient intercept method questions by putting a point at the y-intercept, which is the c, which is -3. And then every time I go to, the gradient is 2, which means every time I go 1 to the right, I'll go 2 up. Then 1 to the right, 2 up. 1 to the right, 2 up. So we can plot these points. There and there, and join them up with a straight line, and you will have the line y equals 2x minus 3. The other one is more of a cover-up method question. So the cover-up method is essentially a trick, but I'll explain why it works in a second. But what you do is you cover up the 4x, and we're left with 5y equals 20. And if 5y is 20, that would mean y is 4. So if you put a point at 4 on the y-axis, and then if we cover up the y bit, 4x equals 20, so 1x equals 5. And if you join these up, you get yourself the line 4x plus 5y. So the reason this works is that what we're actually doing is we're saying on the y-axis, every single point has an x-coordinate of 0. It's 0 something. So over here, if we put in 0 for x, you've got 4 lots of 0, which is 0. So that's why it basically just disappears. That's where the trick comes from. And the same idea applies if you're doing the x-axis, because the y-coordinate's 0, so that disappears. So your solution to this equation is where these 2 points cross. And where do they cross? They cross at x is 2.5 and y is 2. Because the coordinates is 2.52. And that is your answer to that question. Okay, the next one, apologies if it looks all blurry on there. I've taken screenshots off of my laptop. But this was a question from a past paper, I can't remember which one, from the GCSE. And it says, use the graphs to solve the simultaneous equations 3y plus 2x is 12 and y equals x minus 1. So this is actually easier than what I just did. Just read the coordinates of the points where they cross. X equals 3, y equals 2. Done. Probably should put it in the space that they give us. Right, and then the other thing that you can have is you can have ones where you're having to solve a quadratic against a straight line graph. So in some way we need to plot y equals 0.5x plus 8 on here because that's what part A says to complete the table. So if we complete the table, let's go for a half of 2 is 1, add 8 is 9. A half of 1 is a half, so plus 8 is 8.5. Don't know why I skipped out this one. Half of 3 is 1.5, add 8. And once you've done a few, you might notice it's just going down in halves. So we can just fill that in a little bit quicker because you subtract 0.5 every time you go to the left, or add 0.5 when you go into the right. So it says, hence estimate solutions to the following equations. Well, they've plotted x squared plus x plus 2 on the graph for us, and we've just worked out the coordinates for 0.5x add 8. So we need to plot y equals 0.5x add 8 on the graph. Now, you could just use your table. I probably would have actually just drawn this myself. I would have probably just drawn this myself by using the gradient intercept method if the question hadn't prompted the table. Now, because this is a bit of a fiddly graph, what I'd suggest is going through every coordinate that is a definitive number. For example, 0, 8 is easy to read off of here, and minus 4, 6 would also be easy to read off of here because of where the lines are plotted. And if you imagine, we'd also have a 410 because it's just going up in halves. So if you join these 3 points up, you're going to most likely get the most accurate version of this line that you can. One sec. There we go. So that is about as accurate as I can make it, okay? So when it says solve these, there are two answers. There is this point here, which I would say if you go down, looking at this, it looks like that is 2.2. Oops, slightly angled. My approximation there would be 2.2. Is that? I think that's a straight line. 2.2, 8.8. So that is one solution. Another solution is I'd say that is minus 2.7 and 6.6. Because bear in mind that 7 would be there. Now, if this was in an actual GCSE, they would have it printed as high quality as possible, but also they would give you some allowance. So for example, if the answer is 2.2, they would most likely allow from 2.2, 2.1 to 2.3, just to give you a little bit of leeway, and the same for all the other numbers. So your solutions to this are x equals 2.2 and y equals 8.8, or x equals minus 2.7 and y equals 6.6. Okay? hopefully that seems straightforward enough. It's mainly essentially, like I say, just plot the graphs and see where they cross. You will only go as hard as a quadratic in a straight line, but this method does actually work for multiple quadratics. It works for cubics and various other things. The idea is the same no matter how complicated your two graphs are, okay? If anything ever comes up. Okay, hopefully that you found that useful, and like I say, I will do another video for your lesson on Tuesday, so good luck with your booklet, and let me know next time I see you if there's been anything you're confused about.